After running the fine common pharmacophores calculation, we're ready to proceed with the next step, scoring hypotheses. In this step, we'll be employing a user-adjustable scoring function to rank the common pharmacophore hypotheses that were returned during the previous step. The tables in this step are going to be populated as soon as we run the scoring calculation. We'll get started by clicking on Score Actives. Let me give you a little bit of background on how hypothesis scoring works before we run the calculation. As you can see from the Score Actives window that's appeared, the total hypothesis score is the sum of several individual terms. We'll just take a quick look at the terms right now, but for a complete understanding, you'll probably want to refer to the phase user manual. There are three core terms in the scoring function: the site score, the vector score, and the volume score. The site score describes how well common pharmacophore sites from different active ligands align atop one another in terms of RMSD, and the vector term is based on the quality of vector alignments for features like donors, acceptors, and aromatic rings. The volume score is a measure of the overall superposition of each ligand with respect to the reference ligand using van der Waals models of all heavy atoms. There are some additional terms in here as well. The selectivity score is based on an empirical estimate of how rare the hypothesis is. The matching weight term penalizes hypotheses that match a fewer number of active compounds. In this case, we required all of our common hypotheses to match all actives, so this term will have no net effect. The conformational energy term allows you to penalize hypotheses that require ligands to adopt strained conformations. Lastly, you can add in the activity value of what's called the reference ligand. This begs the question of what a reference ligand actually is. A reference ligand is a single conformation of a single ligand whose site locations and orientations are used as the basis for a given hypothesis. Keep in mind that not all of the sites from the reference ligand need to be used. In fact, in most instances, the hypothesis will consist of a subset of sites from the reference ligand. Now, before phase actually proceeds to score our hypotheses, it's going to eliminate those that don't meet certain criteria. The settings for these elimination filters are here on the left-hand side of the screen. The RMSD cutoff filters those hypotheses that do a poor job of matching site alignment across our active set. The vector setting is similar, except it's looking at the similarity in vector alignment. There are some additional metrics that allow us to specify the minimum and maximum number of hypotheses that will actually carry forward to scoring. We can also specify what are called feature matching tolerances for individual feature types. These allow us to give more or less wiggle room when it comes to RMSD thresholds for individual feature types. For example, if you knew that H-bond donors were an important feature, you might wish to lower the RMSD matching tolerance for donor features. Right now, though, we're happy with the default settings, so we'll just run the scoring step without making any adjustments. I'll just click the Start button and submit the job. After the scoring calculation runs to completion, you can see that the hypothesis table is populated with the results, and we can see the scoring results in the survival score column. Furthermore, several new options are now available to us. Before we take a closer look at the list of hypotheses, let's first take a look at how we can adjust the hypothesis score using our knowledge of inactive ligands. To get started with this, we'll click on Score Inactives. As you can see, scoring inactives is relatively straightforward. We'll just be subtracting the inactive score multiplied by a user-defined weight from the survival score that we calculated previously. The idea is that inactive ligands owe their weak activity, at least in part, due to poor alignment with a good pharmacophore model. Thus, we're going to penalize hypotheses that do a good job of matching inactive ligands. I'll run the calculation by clicking on the Start button and submitting the job. Now, at the conclusion of the inactive scoring calculation, you can see that we have the new score present in the survival minus inactive column here. The table is still sorted according to the survival score, but we can sort according to the new score simply by clicking on the appropriate column header. Let's take a quick look at some of the other aspects of the hypothesis table. As you can see, there's a column for every single one of the terms in our hypothesis scoring function, which allows us to get an idea of what the individual components are contributing to the overall score. The only column that isn't populated is the post hoc score. Suppose that, after looking at the individual terms, you were to decide that you had assigned too much or too little weight to a given term and wanted to run a quick rescoring calculation. You could do so by clicking on the Rescore button above. As you can see, in the rescore interface, we can do exactly that. All we need to do is to weight the appropriate terms accordingly, and as you can see at the bottom of the interface, it's also possible to adjust the inactive scoring function as well. Right now, though, we'll go ahead and proceed with the results obtained using default settings, so we'll close the Rescore Hypotheses window by clicking on the Close button. The last couple of buttons up here have to do with clustering common pharmacophore hypotheses. As you can tell, there's a fair number of hypotheses in this table, and it's helpful to cluster them so that we can more easily evaluate diverse hypotheses. I'll click on the Cluster button to get started with this process. Before we launch the clustering job, we see that there are 3 different ways of clustering. You can refer to the documentation for the details, but in general it suffices to know that the default choice, Complete, is generally going to be the best option as it will produce the most diverse clusters. We'll run the clustering job by clicking on the Start button and submitting the calculation. Once the clustering calculation runs to completion, you'll see that the hypothesis table is grouped and ordered according to cluster number, and rows corresponding to sequential clusters are shown in alternating shades of gray. Right now, we're still looking at all hypotheses from all clusters, but what we want to do is just look at a single representative hypothesis from each cluster. We'll do this by clicking on the View Clusters button, and then, in the window that appears, choosing to view only the hypothesis with the highest survival score from each cluster. We'll click on OK to apply these changes. And as you can see, doing so pares the list down so that we're just looking at one hypothesis from each cluster. Now at this point, you're probably wondering exactly what this large empty expanse at the bottom of the interface is. This is the alignment table, and as soon as we look at one of the individual hypotheses above, the alignment table below is going to show us how our ligands align to that hypothesis. Let's see what the alignment table looks like when we place a hypothesis in the workspace. I'll place the first hypothesis in the workspace by checking the toggle next to it. Bear in mind that it's only possible to place one hypothesis in the workspace at a time. You can see that the variant appears in the workspace, and the alignment table below is populated with all of our ligands. However, many of the rows are colored gray. These gray rows are so-called non-model ligands, ligands that were either not in the active set or did not meet the site matching criteria that we specified earlier. As you can see, we can't visualize ligands that haven't been aligned. White rows denote model ligands that have been aligned, and the blue row in particular is used to denote the reference ligand for the given hypothesis. You can see that it's easy to place a ligand in the workspace just by clicking on the diamond next to its name. Also, note that you can include multiple ligands in the workspace by Shift or Control clicking. You're probably wondering how to visualize the non-model ligands in the workspace. We can do that by first clicking on the Alignment Options button here. Then, it's just a simple matter of enabling the option Align Non-Model Ligands and specifying any sites to which we want to force ligand alignment. In cases where no good alignment to at least 3 sites can be found, no alignment will be returned. In this example, let's click OK and proceed without specifying any particular sites that we want to force alignment to. This will take just a moment as Phase calculates the best alignments for the non-model ligands in the table. Now, we can go ahead and place the newly aligned ligands in the workspace. Just to get a feel for how the top and bottom tables work together, let's try including a different hypothesis in the workspace now. As you can see, the ligands that we had previously included in the workspace have now disappeared. If we want to keep ligands visible in the workspace as we view different hypotheses, it's easy to do so just by turning on the Keep Ligands in Workspace option. Let's do that and see how it works. You can see that as we switch between hypotheses with that option enabled, the same molecule continues to appear in the workspace, but the conformation is changed to reflect the change in alignment between the two hypotheses. Now that we have a pretty good idea of how to use the alignment table, let's take a moment to look at the different columns in this table. Obviously, there are the ligand name and activity columns here, as well as this set column that allows us to keep track of whether the ligand is in the active set, inactive set, or neither set. On the other side of the table, there's the relative energy column, which displays the relative energy of the conformer that best matches the hypothesis. The sites matched column indicates how many ligand sites Phase was able to align with the pharmacophore hypothesis. In general, you may see that inactive compounds will match fewer sites. Lastly, the fitness column is used to display the ligand survival score, which is the sum of the individual site, vector, and volume terms. With normal term weightings, the maximum value you can see in this column is 3.0, which is in fact what we see for the reference ligand. Because the reference ligand is used as the basis for the pharmacophore hypothesis, it has perfect alignment with it. Finally, let's take a look at a few visualization tools. At the top of the interface is a toolbar that has some features we can use not just in this step, but also in the subsequent Build QSAR step. This option that's currently grayed out will allow us to turn QSAR visualization on and off later. We haven't reached that step yet, which is why the option is currently unavailable. This adjacent button allows us to turn excluded volume visualization on and off. Excluded volumes are a way of specifying certain regions of space that can't be occupied when aligning a ligand to a hypothesis. It's possible to set up excluded volumes within the scoring step, but it's also possible to do so using other parts of the phase interface, so we'll cover excluded volumes in a separate video. The leftmost button allows us to toggle the visualization of pharmacophore features on and off in the workspace. Finally, the rightmost button in the toolbar allows us to visualize inner site distances and angles in the workspace. There are a couple of steps involved here. Clicking the button will bring up a window that contains tables of all intersite distances and angle measurements. Every possible distance and angle for the displayed pharmacophore is listed here. You can click the All or None buttons to visualize everything or nothing respectively. Viewing everything is a bit of information overload though, so you'll probably find it helpful to Shift-click or Control-click to select a range of specific measurements that you'd like to view. We can export these measurements to a text file, or we can just close the panel, in which case the measurement markers will persist in the workspace. We can turn off the markers by clicking the Measurements button in the toolbar again. Finally, I want to show you how to save selected hypotheses for later use. Although it can be helpful to build a QSAR, it's not strictly necessary to do so, and in fact at this point you're perfectly capable of using hypotheses from the hypothesis table to search for new actives. First, we'll select a single hypothesis in the table. What you choose is up to you, but in this example, I'll sort the table according to the survival minus inactive score, and simply select the top-ranked hypothesis. To add the hypothesis to the project table, export it to disk, or delete it, we need only click the appropriately named button. I'll go ahead and add it to the project table. As you can see here in the project table, the hypothesis has been added as a new entry. We'll learn more about how to work with hypotheses in the project table later on. Right now, though, we'll proceed to the final step in the pharmacophore development workflow by clicking on the button for the Build QSAR step. You can see that only the highlighted hypotheses are carried forward to the QSAR step. It's possible to carry forward more hypotheses, but in the next video, as we learn how to construct a QSAR, we'll work with a single hypothesis in order to keep things simple.